Good day. This work is presented as analysis of light scattering in Cigsse thin-film solar cell through theoretical model in 2D. The study consists of the simulation of a Cigsse solar cell by means of a theoretical model in 2 dimensions. The simulations were made in Silvaco Atlas. The management of light in thin-film solar cells, especially those with absorber layers under 1 micrometer thick, is crucial. Effective light trapping within the active layer while minimizing optical losses in other layers is essential. Optical modeling and numerical simulation have proven valuable for analyzing and optimizing the optical properties of these solar cells. The theoretical model involves layer thicknesses comparable to light wavelengths and textured interfaces to scatter light and extend its path. 2 key challenges arise: accounting for interference effects in models due to the interaction between forward and backward light waves, and incorporating the complex light scattering process resulting from the rough interfaces. Given the random nature of rough interfaces and texture features within the scale of light wavelength, modeling light scattering is intricate. Empirical approaches are necessary to support the modeling and simulation of such optical systems. Numerous teams have showcased Cigsse solar cells featuring CD-free buffer layers utilizing substitute materials like ZNS, in 2S3, etc. Yet, the efficiencies of devices employing these buffers have not consistently outperformed those utilizing traditional CD's buffer layers, which is why simulations can help to understand the behavior of these devices. In this work we improve the Cigsse solar cell theoretically to predict an efficiency of 24.1%. In Figure 1 you can see the structure that we used for the simulations. In this there are 2 films as a buffer layer corresponding to the experimental study that we refer to below. The use of computer modeling for optical design has highlighted the importance of implementing accurate optical models that can account for scattering at rough interfaces. A numerical optical model that takes scattering into account requires input data that describes the scattering of light at a rough interface. By improving our understanding of light scattering and absorption in solar cells, we can develop more efficient and sustainable photovoltaic technologies, leading to a cleaner and more sustainable future. The HT and HR of internal interfaces are calculated by using equations 1 and 2, respectively. These equations relate the Hayes parameters to the interface roughness, which is represented by the parameter in the table. In the table summarizes the Hayes function's optical parameters and the interface's recombination speeds between layers of the solar cell S. P for holes and S. N electrons. A surface-type recombination model defines some interface recombination velocities at interfaces in the modeled solar cell. All recombination mechanisms should be accounted for since they may significantly impact device quantum efficiency. The theoretical model is complemented with the refractive index. The complex comprises 2 parts: the refractive index n and the coefficient of extinction k, which are a function of the wavelength. These vectors are important because they are used. The data for the refractive index complex is extracted from the literature. In the Russell's part you can see the figures. In the second figure you can see the comparison of the JV curves. The red curve represents the experimental study with an efficiency of 23.4%, This work was taken from the literature to validate our theoretical model. This model, with the green curve in the figure, was optimized to match the values of short-circuit voltage, current density, fill factor and efficiency. You can see the comparison of electrical parameters in the table within the figure. In the third figure, a suitable solar cell without roughness in the interfaces is simulated. Demonstrates the external quantum efficiencies curves with and without simulation of root mean square interface roughness. It is observed that the EQE without rough interfaces presents very pronounced peaks throughout the entire spectrum from 400 nanometers to 1100 nanometers. At higher wavelength than 1100 nanometers, the EQE curve is decreased. With this comparison, we demonstrate the importance of entering the optical models as the Hayes function in the theoretical models of the solar cell, which entails a complete study and shows a new approach in the study of the Cigsse solar cell. You can also see the comparison of the external quantum efficiencies of the experimental and the simulated solar cell. In other figures shows 3 images, we can see the diffuse transmittance at various values of root mean square interface roughness mentioned previously. In this figures, it can observe the effect it has no quantum efficiency. It are seen that the changes are more noticeable at different wavelengths. In figure 4, the quantum efficiency increases as the interface roughness increases. The diffuse transmittance and reflectance in the rough interfaces are not desirable because it increases the amount of recombination at the interface. It also generates greater electron mobility at the Cigsse interface and consequently generates a greater shift in diffusion length of the minority charge carrier. This outcome leads to higher values in EQE. Shows that the curves for the Hayes function for h_t begin to grow from 200 nanometers to 1400 nanometers of wavelength, which shows relatively poor photoresponses in the longer wavelengths like the near region. Given that the poor near responses in EQE are often associated with the poor charge collection of minority carriers generated near Mo-back contact. This indicates that much of the Cigsse thickness is inactive and/or possibly contributing to series resistance in the device. In the last figure, a comparison is made between 3 JV characteristic curves. One is the optimization with which we adjust the theoretical model of Cigsse, the second one with second record value, and the next is a prediction only improving the interfaces. The solar cell parameters for prediction value, theoretical value and record value were presented in table inside the figure.